Hello, friends. Now we're going to talk about triple integrals in rectangular coordinates. And in a minute, or depends on when you're watching my videos, but in the future, we'll talk about cylindrical, and we even have spherical coordinates. So what is the deal with a triple integral? Well, triple integrals allow us to solve more general problems. So we use triple integrals just like a double integral can calculate area. A triple integral can calculate volumes of three-dimensional shapes, solids. So we can also find average value with a triple integral, right? Average value of a function. And it's also useful when we study vector fields and fluid flow in 3 dimensions, which comes up in chapter 16. We start to see these triple integrals. So let's just think about what we've been learning about thus far. So far, we've got some region, and on that region, we can choose a point, x sub k, y sub k. And essentially what we do is we maybe subdivide that region into rectangles, and we map those rectangles up to some surface in space, right? And mapping each of those up, that gives us, come up here, this is a really beautiful parallelepiped that I've drawn, but we map all those up and that gives us a volume, right? So we've used double integrals to come up here. We've got that surface being a function of 2 variables, all right? So we found volume that way. So now we are going to think about finding volume. Maybe I've got this little blobby thing here, and this is D. This isn't a surface, this is a 3D region or a closed solid. So D is a closed solid. It's a 3-dimensional region. And so you might see that better maybe if I were to draw a rectangular prism around it and say, we're saying, hey, this D, this is taking up this space, right? It's no longer a surface, it's a 3-dimensional solid. And what we're going to do is we're going to find the volume of all these little cubes inside this solid, and we're going to add those up to find the volume, right? So the idea here when we think about this 3D closed solid, this is no longer a surface, a plane. We're not going to be taking a region and dividing it into rectangles. We're going to be taking this solid and dividing it into sub-boxes or sub-cubes even. All right, so we're going to have some volume, delta V, and we're going to choose a point, x sub k, y sub k, z sub k, in that little tiny point is going to be in each of these boxes. And, I know I've used previous notation with the star. The star just says we don't have to choose it being like the bottom front left corner. It can be anywhere on that box as long as we are doing or finding, I should say, a point inside each of these boxes, right? And so again, that same definition when we're dealing with integrals of making all those boxes smaller. The more boxes, the better the approximation. And so eventually we have infinite boxes, which gives us this exact value. So thinking about this, kind of the idea here, the limit as n approaches infinity of some s sub n. What we're finding is the limit as n approaches infinity as the sum of all of these f of x sub k, y sub k, z sub k, all these output values times delta v. So simplifying that notation, that's like saying the triple integral over d of f of x, y, z dv, or the triple integral f of x, y, z. We're going to say dz, dy, dx. And that's just the most conventional way that we write these. We go down, z, y, x. These are going to have all the same properties and evaluation of double integrals. We're just going to be doing more of them. And so if we think about these D's, right, this D region here, if that D, that solid, is a box, if it's a box, then we would have X between some A and B values. We'll have our Y between C and D, so this makes sense. And I bet you can guess what I'm going to use for my Z. We'll say between E and F. So we will define this more formally, saying that that volume is going to represent the integral from A to B, C to D, E to F, some 3 variable function. So W equals a function x, y, z. We now, actually, I should say 4 variables, but we have then dz, dy, dx. So that's kind of the idea for our setup. That's what we're doing. We are finding all these little boxes inside this solid D, and we're adding them up. Okay, so same idea, it's just adding up lots of little volumes instead of adding up areas and multiplying them by the height. We're adding up the boxes and multiplying them by that 4th variable. So before we really talk about how we're going to define this, which will come in the next video, I do want to do a little example for us. We have in this example a triple integral, and my solid, which I'm integrating across, is defined as the region G. And G is the set of all ordered triples, all x, y, z's, such that x falls between 0 and 1, y is between -1 and 2, and z is between 0 and 3. So let's think about how we would write this integral. So as I'm setting this up, and because this is a cube shape or a prism shape, it's rectangular, the order in which we're integrating, my bounds are all going to be constants. The order that I set this up doesn't matter, but as I said previously, we're going to say dz, dy, dx. That's just the general convention, the rule of thumb, the way we set that up. So in this case, I would find my x values go from 0 to 1, my y values go from -1 to 2, and z from 0 to 3. We would be integrating my function x, y, z squared, and then my order of integration is going to be dz, dy, dx. Okay, so again, just noticing those are my z's, my y's, and my x's. All right, so let's just integrate this real quick just so we see that triple integration is really just double integration, and then we'll define it more formally in the following video. So as I look at integrating this, we start on the inside here. I've got 0 to 1, -1 to 2. Integrating with respect to z, that's going to give me 1/3 z cubed. So I'm going to go ahead and write that. I've got 1/3 x, y, z cubed, and we need to evaluate z from 3 to 0. Again, I'm going to encourage you to say z equals 3 z equals 0, and then I'll write dy dx. Now if I plug in 3, I get 27 over 3, that's 9. Plug in 0, that zeroes this term out. So now I have 0 to 1, negative 1 to 2, 9xy dy dx. All right, now let's integrate with respect to y. So that's going to be a y squared over 2, 0 to 1. I have 9 halves xy squared. We've got y equals 2 to y equals negative 1 dx. Plugging in 2, I have 4, 36 over 2. That gives me 18x. Negative 1, that's positive 1. So 18x minus 9 halves x dx. 18 minus 9 halves, that's the same as 36 halves minus 9 halves. We get 27 halves x. So 0 to 1, 27 over 2x dx. That's going to become 27 over 4x from 1 to 0, which is, of course, 27 over 4. So this really isn't much different than a double integral, but it's just this extra step of having to integrate a third time. We do have a trick we could have used, but this only works where we have these rectangular bounds on all of the sides. So just a shortcut trick, and I think I showed you this in a previous video, but we could have split this up and said 0 to 1 x dx times negative 1 to 2 y dy and times 0 to 3 z squared dz. And that works when I've got this product here and these bounds are all constants. If I had a function in there, I wouldn't be able to do this. All right, so just kind of a shortcut. That will give you the same answer, 27 over 4. All right, I hope you understand that. So in the next video, we're going to talk more about how these, or how this format is officially defined. Email if you have any questions. Don't forget to like and subscribe.